Good afternoon, everyone. My name is Rishika. I am here to present the second milestone video of my project, Remote Sensing with GenAI. This project will leverage advanced machine learning techniques to enhance the interpretation and analysis of the satellite data. Today, I will talk through the components involved, architecture and the business model, the interfaces involved, and also the colorization part, which is the main part of the presentation, and what all models we have completed so far. The solution are front end we are using Flutter, back end I'm using Node server, Node Express, and we are keeping the models in .onnx format, and using Express and Node we are integrating the models with the front end. And then the models which we have now are VGG16 for crop classification and also pix to pix for SAR colorization, and database and authentication it is done using Firebase. The architecture we have is three-tier architecture: client, server, database. The server is the Node Express and the models involved, and Firebase authentication. We have the client, which is the user interaction using Flutter, and then the database we are using the Firebase database. It is three-tier architecture. Now the basic app workflow follows. We need to open the app. Next, if you are a new user, you need to register. If it is an old user, you need to just log in. Then there will be a home screen showing three options: crop classification, circularization. And then if you choose one of them, you upload an image from your local storage, and then you click predict. You get the required output. For crop classification, you get the which class of crop it belongs to, and then for SAR colorization you get the colorized image as output with the ground mask. We have two data sets for each model. For crop classification, we are using a data set from Kaggle, which is having five classes: maize, wheat, jute, rice, and sugarcane. And then for SAR image colorization, we are using Sentinel 1 and 2 data set, which is having two folders. In one folder, we are having SAR images, and in the other folder, we are having optical images. In this also, we have four classes. The interfaces involved are registration and a login screen, which ensures secure user access, home page, which allows user to select between the crop classification and the SAR image colorization, and a dedicated screens are provided for the detailed outputs of these functionalities. On the backend, Node.js handles the incoming requests and communicate with the model, and we are using Firebase to retrieve and process the data. Now coming to the business logic, SAR image colorization. Since these images are very difficult, grayscale, and challenging to interpret, so we are applying the GenAI on these images to convert into colorized formats so that they are understandable. Crop classification. Since here user will upload an image and the model will predict the image, crop image, to which class it belongs to. For example, if it is jute, the output will be like the crop belongs to jute. Now user interaction. Since the user is allowed to upload images via an app with Flutter, he will upload the images and then he gets its results from the model. Data storage. We are storing the user data and securing it and authenticating it using a Firebase. Coming to SAR, synthetic aperture radar, or SAR, this is an active sensor that operates by transmitting the microwave signals towards the Earth's surface and then receiving them back scattered. Earth's Next, this technology is particularly powerful because it works in all the conditions, both during the daytime and during the nighttime, making it very highly reliable for continuous observation. And SAR has broad applications, including we have Earth's observation, monitoring the landscapes, vegetation, urban development, and also the military surveillance, like providing high resolution images for security purposes, and also environmental monitoring, tracking the deforestation and natural disasters, ice sheet movements, etc. And coming to planetary explanation, we are mapping the surface of other planets in detail. So SAR, it is an ideal sensor to observe the Earth's surface both daytime and nighttime in all the weather conditions. Now coming to the basic idea regarding the image colorization, it is the process of adding colors to the grayscale or black and white images by mapping the intensity values to a color space. This technique transforms the dull or hard to interpret images into visually appeal images, meaningful representations, like they are understandable easily. There are several methods which are used for image colorization, including image segmentation, dividing the images into regions to apply specific colors, texture synthesis, using patterns to generate realistic textures and colors, machine learning techniques, automating the colorization process based on the patterns. Advanced neural networks like convolution neural networks are important in this field. This they predict the missing color channels by training on large datasets of paired grayscale and color images. Generative adversarial neural networks, which is the GANs which we are using in our model, take it further, where a generator creates the colorized images and a discriminator evaluates their realism, pushing the generator to improve iteratively. Basically, generator is trying to fake the discriminator, and the discriminator is trying to know whether the generator is generating fake images or not. With recent advancements in deep learning, we now achieve high quality, realistic images results, making the colorized images useful in fields like media restoration, SAR image colorization, etc. Now coming to the main crux of the project, the SAR image colorization and the need for colorization. SAR images are typically grayscale images as we told in before, because they capture the radar backscatter intensity rather than the visible light. That's the reason they are not understandable clearly. They are very hard to understand. And while this makes them highly reliable for various conditions, their interpretations can be challenging, especially for the users who don't have expertise in this field. So why we need to do SAR images? Why we need to colorize the SAR images? Because we need to enhance the interpretation. We are assigning colors to different intensity, backscatter intensities, to make it easier to identify and differentiate the key features such as water bodies, vegetation, urban areas. And also for visualization purpose, colorization will improve the visual appeal and accessibility of them, making them more usable for the users with the technical expertise. Analysis, it supports the comparative studies and enables the detection of specific patterns or anomalies such as flood affected regions or deforestation trends, etc. How will this be achieved? We are doing in this in three methods. Dataset, we are using paired SAR and optical images sourced from Sentinel-1 and 2 dataset, which is from Kaggle. And then the SAR images provide the grayscale radar data, while the optical images serves as the ground mask for the colorization. Model, a cycle GAN model is trained to map the grayscale images to the optical images. It is ideal for this task as it learns to translate the image domain without requiring any perfect alignment. Output, a realistic colorized image that closely mimics the natural scenes, providing both realism and. Now coming to pix-to-pix GAN. GAN is nothing but generative adversarial network. It is a type of deep learning network that can generate data with similar characteristics as the input training data. It is a powerful deep learning technique. They are widely used in applications such as image generation, image colorization, style transfer, etc. How do these work? GAN consists of two networks that train together in a competitive process. We have generator, we have discriminator. Coming to the generator part, the generator takes a random vector as input and produces the data that mimics the structure of the training data. Its goal is to create realistic outputs that can fool the discriminator. Coming to the discriminator, it receives the mixed batches containing both real data and the fake data. Real data that is not from the training data set and the fake data from the generator. It classifies each observation as either real or generated, acting as a quality checker, quality control mechanism for the generator's output. Coming to the training process, the generator improves by learning to create data that the discriminator cannot distinguish from the real data. Simultaneously, the discriminator also becomes more skilled enough to identify the generated data, pushing the generator to improve further and further. This adversarial feedback loop leads to data, uh, increase the realisticity in the data. Coming to downsampling and upsampling. Downsampling reduces the spatial dimensions like height and width of an input while increasing its depth. This process helps the network to extract the high level features and reduce the computational cost. The components of a downsampling block is nothing but convolution layer. It applies filters to extract the features, and batch normalization. It normalizes the output to stabilize the training data and speed up the convergence. And ReLU activation, a nonlinear function which is used to introduce the nonlinearity. By default, leaky ReLU is used in pix to pix. Instead of completely zeroing out negative values, which ReLU does, leaky ReLU allows small negative values through using a slope of 0.2. This prevents neurons from dying, that is becoming inactive. Coming to upsampling, it increases the spatial dimensions of an input, essentially reversing the downsampling. It is critical for tasks like image generation, where the goal is to produce high resolution outputs. Differences between downsampling and upsampling blocks. Dropout layer, some upsampling blocks add a dropout layer to randomly drop a fraction of neurons during training. This prevents overfitting. An activation function, the upsampling block uses ReLU, which outputs 0 for the negative values, like all the negative values are not considered, making it different from leaky ReLU, where some negative values are considered to make sure that the neurons are not dying, which is used in downsampling. The transpose convolution, instead of a regular convolution, upsampling uses transpose convolution, which effectively increases the spatial dimensions of the input. Batch normalization, it is also present just like in downsampling blocks. Dropout in pix to pix, to improve the generalization, some upsampling blocks in pix to pix randomly drop the connections during training using dropout. Why these choices are important in pix to pix? Because downsampling, it helps the network to compress the input images into a feature representation that captures the important information for the task, whereas in upsampling, it ensures that the output image is highly resolutional, and also it matches the target image size. Whereas leaky ReLU and dropout, it enhances the stability and avoids overfitting, and also it makes the network more robust. Now coming to generator, it follows a unit-like architecture. The key features of this architecture include the encoder-decoder structure and the skip connections. Encoder is a subnetwork where the input image is encoded into a low-dimensional representation, whereas decoder is similar to encoder but takes the low-dimensional representation and reconstructs it to bring it back to the original spatial dimensions. Skip connections, it transfers the activation from corresponding layers in the encoder to the decoder. The encoder consists of 8 downsampling blocks, and convolution, it uses 4 by 4 filter with a stride of 2, And the encoder expects an input shape of n comma c comma 256 comma 256. At the end of the encoder, the output shape is n comma 5 12 comma 1 comma 1. Decoder. The decoder consists of 8 upsampling blocks with the following structure, and the number of channels is doubled in the decoder due to the skip connections, and also the decoder expects an input shape of n comma 5 12 comma 1 comma 1, which is the output of the encoder. Now decoder, at the end of the decoder, the output shape is n comma 64 comma 256 comma 256. After the last layer in the decoder, a convolution is applied to map to the desired number of output channel, followed by an activation function. Now coming to the next part, which is the discriminator. Discriminator in Pix2Pix, it is a patch GAN, a specialized type of discriminator which focuses on classifying the image patches rather than the entire image. Here, patch-based evaluation means it, instead of judging the entire image as real or fake, patch GAN divides it into smaller patches. Each patch is classified as real or fake, providing localized feedback to the generator. Next, patch-GAN uses a series of convolution layers to process the patches. With each convolution, the respective field grows, enabling the discriminator to make decisions based on the larger portions of the patch. Now, variable depth, it is the number of layers in the patch GAN, depends on the size of the patches being evaluated. Smaller patch sizes require fewer layers, whereas the larger ones require more to cover the patch area. The discriminator output is a grid where each value corresponds to the classification of a patch as real or fake. So the output is a grid where each value in the grid represents whether the patch is a real or fake. Now coming to the architecture, the above portion indicates the generator part and the below portion is the discriminator part. Basically, generator is transforming an input image into a generator output image. So the input image is having like 5 by 512 by 512 by 3 size, which is the actual image. It undergoes downsampling where at each where at each position its resolution is progressively reduced via convolution layers. The red color arrows indicates the convolution layer. Here the kernel is 4 by 4 and the stride is 2. Next, next at the bottleneck, that is the center of the generator, the smallest resolution, that is the 2 by 2, it captures the high level features. The features are then upsampled. Here they are upsampled via a deconvolution layer. That is, blue arrows indicates deconvolution. It is having a kernel of 4 by 4 and a stride of 2 to reconstruct the output image with the same resolution as that of the input image, that is 512 by 512 by 3. We are using skip connections, that is black arrows. They directly connect the corresponding downsampling and upsampling layers. We are giving a connection between the upsampling layer and the downsampling layer. Why? Because to retain the spatial information, to prevent the loss of the finest amount of details, output a generated image that is with the same dimensions as that of the input. Now discriminator, bottom part. It distinguishes between actual images and the fake generated, that is the fake images. Both the real image and the generated image is given to the discriminator. That's why it is 512 by 512 by 6. The discriminator processes those images through a series of downsampling layers. The purple block indicates the downsampling block, progressively reducing their resolution while increasing the depth. We are reducing the resolution and we are increasing the depth of the feature maps. The final output is a decision whether the input is real or generated. Basically, the model which I have trained, it is for 110 epochs. For 110 epochs, this is the screenshot of the epochs. We are getting the loss, everything display. Coming to FID score, it is a score which evaluates the performance of the image model. FID stands for Frechet Inception Distance. It evaluates the similarity between the real and generated images by comparing by comparing the feature distributions. It uses a pre-trained model to extract the image features and computes the differences in the mean and the covariance. Basically, a lower FID score indicates the performance of the model is very high, whereas a high FID score indicates that the performance of the model is a little less. It indicates that there is a close relation between the quality and the FID score. It is used to assess the quality and diversity of the generated images in tasks like SAR image colorization, etc. We compare the colorized images with the corresponding real optical images, then extract the features using a pre-trained model and calculate and compare the mean and covariance of the feature distributions. It measures both the quality and diversity. Basically, the performance of the model is evaluated using FID score. Here is a basic code snippet of my code calculating the FID score of my model. Since the model is trained for only 110 epochs, the FID score which we got is very high. It is close to 500. So we will further improve the model by increasing the number of epochs for some 190 epochs, so that we will get the FID score in within the range 150 to 180, which is a very good score. Now this is the basic outputs we got. The first row is nothing but it is the SAR images, and the second row is nothing but the ground truth, that is the actual optical images, and the third row are the generated images from our model. So we can see the difference between the ground truth and the colorized image. There is a slight difference because our model is not trained for not many number of epochs, so we are getting somewhat a blur image. So if we increase the number of epochs to 250 or 220, then we will get a very clear image which is almost equal to the ground truth. Basic workflow, we are defining the data set. We are loading both the paid SAR and optical images using a dataset class in PyTorch. Then we are initializing the model. We are setting up the pix-to-pix model architecture. Next, we are setting up the parameters like the batch size, loss weights, learning rates, etc. And then we are preparing the data. We are mapping the SAR and the optical images. Then we are training the model, that is train the discriminator to distinguish the real and fake images, and we need to train the generator to minimize the adversarial loss. Next, the save points. We are periodically saving the .pth files of discriminator and the generator, so that if we lose the track of training, then the last saved file we can use. Next, we are generating the output using the pth file. We are using to colorize the SAR image, and then we are validating the model, that is the performance of the model is evaluated using the FID score. Here is the video snippet of my Flutter app. We are logging in and then we are trying to upload an image, and then we are clicking on predict. We are getting the colorized image along with the ground truth value. These are the sources of information, the links, everything we have used for building this model. Thank you for everyone for taking your time and listening to this video.